Hello everyone, this is part 3 of polar coordinates, the final topic in the final lecture in this course. I'll be doing some review somehow. I haven't decided exactly how, but just keep checking your T-Wolves email and your Blackboard announcements in the course, and you'll know exactly what's going on. So, area and polar coordinates, that's our final topic. You can see on the final exam topic sheet that I've been referencing, under polar coordinates in part 3, area and polar form, there's going to be one question worth 8 points. So we have a theorem, but before we get to the theorem, the idea behind polar coordinates is, well, if you recall in the Cartesian coordinate system, when we had to find area under a curve, what we did was, so if we wanted the area between, let's say, the graph of a function and the x-axis and the vertical lines, x equaling a and x equaling b, what we did was we used little strips that were of differential dx in width, and we used the concept of Riemann sums to create the definite integral that gave us the area under the curve. Now, with regards to polar coordinates, first off, consider a circle, say for simplicity centered at the origin. We know the area of a circle is pi r squared, but if we want the area of, let's say, a sector, so a little piece of the circle, like a piece of the pizza pie, right? Say sweeping through an angle of theta, then it's basically going to be the ratio of theta over 2 pi. That's how much we have is that portion theta of the entire portion of the circle. So theta over 2 pi times the area of the circle, which gives us the area of the sector to be the formula. I'm just showing you a way to memorize, to create the formula, 1/2 theta r squared. So the idea is basically, instead of having these differential strips of dx in width, we're going to have these differential sweeps, so to speak, of differential d theta. And then we consider again the Riemann sums. So I'm not going to go through the formalities of all of that, but that's the basic idea. And we come up with the theorem. So the function does have to be continuous and non-negative, just like the Cartesian. And we use alpha and beta. So this is the Greek letter alpha, lowercase alpha, and this is the Greek letter beta, lowercase beta. And we've got a graph, r equals f of theta, and you've got the radial lines, theta is alpha and theta is beta. And then here's the formula. I would say remember it and write it down on your cheat sheet, because obviously you're going to need it. Probably remember it in this form, 1/2 integral alpha to beta of r squared d theta. But you could use the functional notation form as well. Okay, so a couple examples. Find the area inside. Now, I'm giving you the radial lines, and these are basically the poles. Okay, if you were to take this equation, solve it for r, you'd come up with plus or minus the square root of 8 sine of 2 theta. You don't need to do this, but I'm just showing you. And then you would actually have to find the poles, maybe by creating a table of ordered pairs. Like, for example, if you plug in 0 degrees, you actually get 0. And that's a pole. That's considered a pole, analogous to an X-Intercept. So you're going to want to find these poles, and what you would do is you would go through and graph the function, maybe pick 15 degrees, because you want this to be, the 2 theta to be a multiple of 30. You come up with plus or minus 2. And you go through and make a list of all the ordered pairs, and once you get to 90 degrees, that's when you get another 0 or another pole. So that's why the values of alpha and beta are 0 and pi over 2, which is 90 degrees, because those are the poles. And the graph of this, you won't have to, I'm going to give you the graph, and I'm going to give you the radial lines that I want you to use, so you don't have to worry really about any of what I'm doing over here. The graph of this actually looks like that, okay? Where this point right here is actually at 45 degrees. Let me squeeze this in here. And it's the square root of 8. Okay? So this would be 0 degrees, 90 degrees, 180, and 270. But all you really need to worry about, so in terms of the radial lines, this is alpha equaling 0 and beta equaling pi over 2. And you do have to leave the radial lines. Oh, I'm sorry, I didn't notice I graphed that without you guys seeing what I was doing. So that's what the graph looks like. And I mentioned this point, the square root of 8. And you do have to leave these radial lines in terms of radians, okay? But all you need to do is really plug into the formula. So if you write down this formula, obviously on your cheat sheet, 1/2 integral alpha to beta r squared d theta. We'd have 1/2 integral, okay, everything's a given. Alpha is 0, beta is going to be pi over 2. Okay, so all we need to do is plug things in. We got 1/2 integral 0 is alpha, beta pi over 2, and the r squared is 8 sine 2 theta, and that's with respect to theta. So then it's just a matter of evaluating this integral. So 8 times 1/2, I'll bring out the 4, integrate sine of 2 theta, we get integrating sine, we get negative cosine, and because of the argument 2 theta modified by 1/2, so that's our linear argument rule, recall. So negative 1/2 cosine 2 theta, and that's evaluated from 0 to pi over 2. And so this gives negative 2 cosine, I'll just take it slowly here, cosine 2 theta evaluated from 0 to pi over 2. And so now upper limit of integration goes in, so negative 2 cosine 2 times pi over 2 is pi, and then minus lower limit goes in, so minus 2 cosine of 2 times 0 is 0. If you want to change the degrees, you can. That'd be minus 2 cosine 180 degrees, and then let's say plus 2 cosine 0 degrees. 0 degrees, same as 0 radians, but there is a distinction, of course, denoted by the degree symbol. And so then we get negative 2 times cosine of 180 is negative 1, and then plus 2, cosine of 0 is 1, so it looks like 2 plus 2, or 4. So that's the area inside this one petal here. Okay, so then for a final example, this is the type to expect on the final exam, hint, hint. And it's a little bit more work, but it's very important, and this is a great problem, so definitely expect to see something similar. First off, with the graphs that you will be supplied, you won't need to show the table or the poles, or you'll be given, as you are here, the radial lines. But the table, the way these radial lines were determined, theta and r, 0 degrees, plug in a 0, sine of 0 is 0, so that's a pole, so that's why 0 is one of the radial lines. You go through and get more. I'll just do a 45 degree one here. That's the sine of 90, which is 1 times 3 is 3. And then at 90 degrees, sine of 180, that's 0. That's another pole. Okay, so the graph of this, okay, so here's 0, 90, 180, and 270. Okay, we do have to pay attention to this one little setup point. It says inside the graph. We'll address that at the very end. But the point is that this is the graph. It's a Rose curve, just like the one we had graphed formally. And this is actually the point pi over 4, 45 degrees. Let's see, r and theta, excuse me. So r comes first. And 45 degrees. And these are the radial lines. Alpha equaling 0 and beta equaling pi over 2 again. Okay, so what we're going to be finding is the area inside this one petal. And so therefore at the end, since we want the area inside the entire graph, whatever that area is, we're going to have to multiply it by 4. So that's just a subtle point. Okay, so the area of the one petal. Okay, we know the formula, 1/2 integral alpha to beta, r squared d theta. Okay, so we get 1/2 integral. Spread this out a little bit. I'm definitely going to have enough room here. So the area integral 1/2 integral alpha was 0, beta pi over 2 again. But now we've got r squared, and r is 3 sine of 2 theta. But that has to be squared with respect to theta. Okay, so when we square that, we square the 3 to get 9 times the 1/2, so I'll bring 9 halves out in front. Then we got the integral from 0 to pi over 2 of sine squared of 2 theta with respect to theta. And this is what makes this problem an excellent problem for the final exam, because what we have here is an even power of sine. Even powers of sines and cosines come up quite frequently in applications as you go on in your engineering. If you're taking engineering, even differential equations, sine squared and cosine squared appear quite often. And if you have to integrate them, then you might recall what we need is what I like to refer to as the double angle / power reducing formulas. And we have 2 of them. For sine squared of theta, it's 1/2 times 1 minus cosine of 2 theta. So recall this from exam 3, where the angle is doubled and the power is reduced. And then we do have one for cosine squared theta as well. 1/2 times 1 plus cosine 2 theta. So you might want to consider writing these two formulas down, because I'm giving you an example with sine squared, and I promise you your problem's going to, on the final exam, is going to be similar to this, and you could probably guess that you might get something that involves a cosine squared. So make sure you include those formulas on your cheat sheet. Okay, so we replace sine squared by the identity. So 9 halves integral 0 to pi over 2. Okay, 1 half times 1 minus, and then it's the cosine of twice the angle. So we have to double this angle 2 theta. So that becomes 4 theta with respect to theta. Now, just to make all the integrations clear and everything simple, I'm going to separate this into two integrals. First off, multiply the 1 half times the 9 halves to get 9 quarters. And then we've got the integral from 0 to pi over 2 of 1 with respect to theta. And then minus 9 quarters, the integral from 0 to pi over 2 of cosine 4 theta with respect to theta. Now you can do the calculus any way you want. I just chose to split it up into two integrals. If you want to keep it as a single integral, that's fine as well. Okay, so here integrating 1 with respect to theta, we get theta. That's evaluated from 0 to pi over 2. And then we have the minus 9 quarters, and then integrating cosine of 4 theta. There's our linear argument rule again. So 1/4, cosine becomes positive sine, so 1/4 sine of 4 theta, and that's evaluated as well from 0 to pi over 2. Okay, so each one separately, 9/4 upper limit, pi over 2, minus lower limit, 9/4 times 0. And then let me do it this way. Let me say minus 9/16, and then I'm going to open up brackets and do sine of upper limit goes in. So sine 4 times pi over 2 would be 2 pi. And then minus lower limit goes in. Sine of 4 times 0 is 0. Okay, so then we have sine of 2 pi, which is the sine of 360. That's equal to 0. Sine of 0, also equal to 0. 9/4 times 0 is a 0. So we just get 9 pi over 8. So recall that's the area of just that one petal, or the total area. It's going to be 4 times that. So 9 pi over 2. Alright, so that's it. That is the end of the course. I do not need to show you anything new. And I'm going to have some more videos for you to kind of review, or at least guide you in the right direction. So keep checking your T-Wolves email and your Blackboard announcements, and I wish you all the best of luck, not only on the final exam, but in all of your future academic endeavors.